Okay, so let's scoot on. Let's talk about polar equations and graphs. Before we get into all of that, I want to expand a little bit on a previous lecture we did with polar coordinates. Now, the polar coordinates, if you remember, have the format of r comma theta, right? R is the distance from the pole to the point, and theta is the angle. Well, we were graphing all of that based upon just graphing the pole and then the polar axis. Well, now we have the polar grid system, and I want to talk about this for a few minutes. You know, we have our XY axis, and on our XY axis grid system, we have the x-axis, we have the y-axis, and we have our coordinates. We have the coordinates x comma y. So we go either left or right, however many units from the origin, right? And then after we go left or right, we go up or down. So if you recall on graph paper, these are just squares that we are working with, nothing fancy. The polar grid system is a little bit different. I still have two axes, right? But I am talking about angles. So each axis actually represents the typical radian measurements. We have 0 radians, pi over 2, pi, 3 pi over 2, and then back to 2 pi. Now, I don't have these grids to make up squares. What I have is these concentric circles. And these circles are representing R. Okay, so understand that. These circles are representing R. So if I was asked to graph the polar coordinate 2 comma pi over 4, then remember, the 2 tells me the distance away I am from the pole. Well, now that we have the full grid system, the 2 is telling me I'm on the second circle, because that's 2 spaces, or a length of 2 away from the pole. And I'm at the radian measurement of pi over 4. So from 0, we're going pi over 4, and this is going to be where that point is located. It's on the second circle, pi over 4 radians away from the polar axis. Are you with me? Now we have the complete grid system. Again, it is the 2 represents the distance from the pole to the point, and on the full grid system, it's that second circle. And the pi over 4 is the radian measurement from the polar axis. So into quadrant 1, pi over 4. So we're on this second circle. If you put it here, that's incorrect because that's the third circle. So that would have been 3 comma pi over 4. So be very careful about that, okay? Okay, we are going to start graphing polar equations. And in order to graph them, it's actually going to be best for us to convert them into rectangular equations. Now, we spoke about that in the previous lecture with polar coordinates. So if you need to refresh your brain a little bit, go back and refresh your brain. And I'll be right back. Okay, so let's look at this first equation. They're asking us to graph this polar equation. Now, in order to graph it correctly, we're going to need to take this polar equation and convert it to a rectangular equation. Again, I suggest that you look back at that polar coordinate lecture that I did before, because it shows us how to convert between the 2 different equations. I put these items up here to remember, because that's what we're going to be using. The fact that cosine of theta equals x over r, sine over theta is y over r, and x squared plus y squared equals r squared. Okay? So there's probably a couple of different ways that you can start converting this. This is what I'm seeing. I'm seeing that I can take the cosine of theta and make it x over r. With me? By the way, before I get too far into this is in polar form, which means my points are r comma theta, right? I want to transfer them into x's and y's. I don't want r, I don't want theta, I want x and y. Got it? Okay, just checking. Now, so I'm seeing that the cosine of theta is x over r, which means I'm going to make a replacement. So I'm going to say r equals 2, and instead of saying cosine theta, I'm going to say x over r. Got it? Okay. And then I'm going to simplify it. I don't want to have a denominator here, so I'm going to multiply both sides by r, which will give me r squared equals 2x. Good? Okay, and if you're like, wait, I didn't see that. Well, this right side would just be 2x over r, wouldn't it? So I multiplied both sides by r, got rid of that denominator. Cool? Okay, now r squared I can replace, can't I? I can replace it by x squared plus y squared, can't I? Okay, looking pretty good. And now here's the deal. I'm noticing I have an x squared and a 2x. That kind of triggers something in me that triggers that we should move everything to one side. And when I do this, if I just for right now focus on these two x's, if I complete the square on these two x's, so to speak, I would have a single parenthesis with an x inside it being squared, as opposed to two different x's floating around. With me? So again, if I complete the square on this, I'll get that perfect trinomial. Well, I have something times itself. But the deal is I'll have x written only one time as opposed to two times. So, to complete the square, I need to make sure the lead coefficient's a 1, which it is. There's no third term, so I'm going to create that third term for the x's. And so remember, to create that third term on the x's, we are going, and this is for our x's, we are going to take the -2, which is a coefficient of x. We're going to take half of it, and then we're going to square it. And when you do all this work, you end up with a +1, right? Which means my equation is now looking like +1, because I have to add it to both sides, right? Now this is a perfect trinomial, so when I factor it, it looks like this factor. Here's the deal. I have x written only one time now, which is exactly what I want. I have x written one time now. Cool? Okay. And now you're like, great, what is this? Well, this is almost looking like this x squared plus y squared equals r squared, right? Remember, r was the radius? Correct. So if that's the radius, believe it or not, this is a form of a circle. And we're going to get into circles in a little bit more in another lecture. And if you want to go ahead and look at that lecture, that's fine. Circles are actually quite nice for us. But this particular circle, and I'm going to write it over here, this particular circle has a center at +1, 0, and has a radius of 1. I had to take the square root of this. Okay? And let me show it over here. I have to take the square root of this 1. And the square root of 1 is just 1. Okay. So now, I'm going to graph this. By the way, remember, it was a polar equation that I was graphing. So I'm graphing it on the polar grid system. So remember this. You're graphing it on the polar grid system. Got it? Okay. So now, remember, the center was at 1, 0. So that would be here. And my radius is 1, which means I'm going to go up 1, right 1, down 1, and left 1. I know you're like, you're on the polar grid system. I know I am, because the equation was a polar equation. And I'm actually graphing this polar equation on a polar equation grid system. When I changed it to rectangular form, I can see what it looks like a lot better than just trying to punch in a bunch of numbers here to figure it out. when I do this, I end up with this circle being graphed on this polar grid system. Let me get rid of this middle dot. So maybe it makes it a little more obvious. The graph of this polar equation, r equals 2 cosine theta, looks like this circle with the center at 1, 0 and a radius of 1. Cool? Okay, hang in there. Got another one for us. Okay, so let's look at the second one. Now I left this information up here so we can see what we're working with. I have r equals 2. And you're like, well, how the heck do I do that? Okay, so there's a couple of different approaches. I could replace r, right? All I have to do is take the square root of both sides, and r would be equal to the square root of x squared plus y squared, wouldn't it be? So let's do that, because we can see that, right? We know that if we take this equation and square root both sides, r would be equal to this equation, wouldn't it? But I'm not liking a square root in there, are you? Okay, so if we square both sides, then we would end up with x squared plus y squared equals 4. Agreed? Hey, that's something we can work with. That's actually pretty easy. That looks like this, doesn't it? Okay, so remember what I mentioned before in the previous problem. This is actually an equation of a circle because r stands for a radius. So this is the x direction and the y direction. So here's the cool thing about this one. This actually tells me my circle has a center of 0, 0, because there's nothing attached, and it has a radius of 2. Take the square root of 4, you get a radius of 2. Are you with me? And again, if you need to refresh your brain, or you're like, I've never learned about circles, go to that lecture on circles, okay? So, remember, but I'm graphing a polar equation, which means I'm graphing it on the polar grid system. So, let me get my polar grid system here. Okay, so according to this information, my center is 0, 0, and from there I go out 2 spaces. And when I connect my dots, the graph of that polar equation is actually this circle. It's actually the second concentric circle on the polar grid system. Cool? Okay, I got another one for us. Let's look at this third problem. It is r sine of theta equals 2. Okay. So again, we need to convert it to rectangular because it's easier for us to see and work with. So in this particular case, sine is y over r, isn't it? Which means I just get y equals 2. All right. So let's take a look at this. Here's my grid system, right? Y equals 2 is what kind of line? Yeah, this is a horizontal line crossing at 2, isn't it? Well, if this were the y-axis, and here's the 2, this is what this graph would look like. Right here. This would be your y equals 2. It is just a line, horizontal line, crossing at that second concentric circle, like on the positive side of it, correct? Through 2. This is just a line. This one is a circle. Just like the previous one was also a circle. By the way, this was r. Remember r was the distance away from the pole? Well, 2 spaces away all the way around does give me a circle, doesn't it? So in my mind, I could almost think, well, this is a circle of radius 2, which is exactly what we came up with. Cool? Okay, so hang in there. I've got a couple of theorems for us that actually go with these 3 examples that we just worked with. Okay, so let's take a look at this theorem. This theorem says, let A be a positive real number, then. So they've given us 4 cases here, and here's what I'd like you to notice. These 4 are very similar to each other. Notice it says r equals 2 times a times the sine of theta. The second one has a negative in front of it, but it's the same as the first one. Numbers 3 and 4, instead of sine theta, have cosine theta. Correct? Okay. Notice something, though, about what they all say. All 4 of these are circles, right? Now, they tell you on number 1 that it's centered at 0, comma, a. And in number 2, it's centered at 0, negative a. But numbers 3 and 4, a is in the x-coordinate position and negative a is in the x-coordinate position. And they all say that they have a radius of a amount. So remember, radius is always positive, which explains why all 4 of them say r equals a. Now, here's the deal. Sine is y over x. Pardon me. Sine is y over r, isn't it? So sine kind of represents the y-coordinate, doesn't it? Well, notice the a is in the y-coordinate position. Same thing on number 2. We're dealing with sine, which represents y, and the negative a is in the y position. There's a negative in front here. Okay? On numbers 3 and 4, we're dealing with cosine. Well, cosine refers to the x, doesn't it? Notice the a is in the x position. Is it not? Okay. Now, if you go back to the first polar that we graphed just a few minutes ago, it said r equal 2 cosine of theta, didn't it? Well, that looks like this one, doesn't it? This one right here looks like example number 1. Example number 1 said r equals 2 cosine of theta, doesn't it? So in this case, a is supposed to be right there. Do you see it? Yeah, a is equal to 1, isn't it? If you go back and look at the work we did, based on this theorem, we should have come up with the center of 1, 0. Did we? We certainly did. We had to go complete the square to find it, but we came up with the center of 1, 0, didn't we? We also found that the radius was 1, and according to the theorem, the radius should have been 1. So, doing the work on problem number 1 has verified this theorem for us. Does that make sense? This theorem, remember, theorems only come about based upon the work we do. And if the same thing happens over and over and over again, every time we do problems that look like these, then there's a pattern. And a theorem means it's worked every single time. There's nothing to disprove it. So anytime you have these particular formats, you know you're going to be coming up with a circle. It's just where's the center of the circle? Am I dealing with sine? Then that a is going to be in the y position. And if there's a negative in front, it's a negative a. Am I dealing with cosine? Then my a is in the x position. And again, if there's a negative in front, then the negative goes with the a. But in all 4 cases, your radius was just a. Good? Okay, so I've got another theorem coming up that's going to work with example number 3 that we did just a few minutes ago. So stay tuned. Okay, so let's look at this next theorem. It says let a be a non-zero real number. The previous theorem said a was a positive number. So remember that. This one is a non-zero real number. So clearly it can't be 0, and a real number could be fractions, decimals, negatives, and positives, right? So there's a difference between the 2 theorems start. So go back and take a look at that. Then the graph of the equation. Now they've given me 2 equations here. This one looks like example number 3, doesn't it? Because example number 3 had r sine of theta equaled 2. And when we converted it to rectangular form, we got basically y equal 2, didn't we? Which was what kind of line? A horizontal line, right? Okay, so horizontal lines go like this, and they cut through the y-axis, don't they? Well, think about it. Sine of theta represents y, or I should say sine represents y, doesn't it? So check it out. This type of equation is a horizontal line. Horizontal because it cuts through the y-axis. Sine represents y. And it's a units above the pole if a is greater than 0. In our example, we had a equaling 2 in example number 3, didn't we? Well, didn't we get a horizontal line 2 units above the pole? Excellent. So this is backing up the work that we've done, right? Now, if a is less than 0, then the line lies. Remember, the only reason absolute values are here is because it's representing the distance. Then the line lies that many units below the pole. So if in our example a was -2, I'd still get a horizontal line, but instead of being above the pole, I'd be below the pole 2 units. Cool? Okay, this next one has cosine in it, doesn't it? Cosine refers to x. Agreed? Well, check this out. X, it's a vertical line because vertical lines cross the x-axis, don't they? So when it has the cosine in it, we get a vertical line. And it would be a units to the right of the pole if a is greater than 0. And if a was less than 0, then it's going to be that many units away from the pole, but to the left of it. Again, the absolute value tells you it's the distance. Cool? Now, these first 3 examples we did were very easy to turn into rectangular equations and graph them. But you know, we're going to have some polar equations that are not so easy to turn into rectangular equations. So unfortunately, we're going to have to leave them as polar equations. What's going to help us, though, is seeing if there's any symmetry to the polar equations. Because if there is symmetry, then I know that some of the points that I find, if there's symmetry, I know where the other points are going to lie. So example, if you recall from a previous lecture, x-axis symmetry means points that are up here will also be down here, right? Y-axis symmetry said points that are over here would also be over here, right? Origin symmetry said points that are here are also going to be over here, aren't they? Well, that symmetry is going to apply to polar equations, and that's what we're going to look for when the polar equations are not so nice to try to turn into rectangular equations. So okay, so let's look at these different symmetries. First thing I need you to remember is this. I need you to remember that we have, in our polar, we have the point r comma theta, right? We have been able to convert these back and forth between polar and rectangular. And in rectangular form, it's x comma y. So if you notice, r is in the place of the x and theta is in place of the y. Agreed? Okay, so I need you to kind of keep that in your mind. By the way, if you remember the symmetry we spoke about in another lecture, and if you were actually in my class, it's section 2.2 in the pre-calc class, a lot of these are going to sound familiar. So I have the video. Go back and take a look at the video for symmetry. Now, here's the deal. In order to have polar axis symmetry, one thing I need you to remember is this. Here is my polar coordinate system, right? My polar axis is this guy right here. This is the polar axis. That is basically the x-axis, isn't it? So, notice what it says. Replace theta with negative theta. Well, theta is in the place of y, isn't it? And you're replacing it with like a negative y, aren't you? And I know some people aren't going to appreciate going back and forth and saying, well, how can you relate the two? But you can relate the two. If you can kind of picture this polar with the rectangular, then it's going to be very good visually speaking to bring something you already know into this new topic and to realize this new topic is basically the same as what we've already done. Okay? So, the polar axis is basically the x-axis in rectangular. we're replacing theta with negative theta, or y with negative y, like we did in rectangular. If an equivalent equation results, then the graph is symmetrical with respect to the polar axis. So for instance, if I have this point, r comma theta, and I replace theta with negative theta, right? And if I get an equivalent equation, then what that tells me is that I am going to get this point down here, which is symmetrical about the polar axis. You with me? This is what it would look like on the graph. It would be symmetrical about the polar axis. Cool? Okay. Now, let's look at the line theta equals pi over 2. Well, again, if you look at your graph, isn't this where theta equals pi over 2? It's basically the y-axis, isn't it? Okay. And we're replacing theta with pi minus theta. You're like, wait, why pi minus theta? Hold on. So, I once again have this point, and I'll put it right here. And I have, let's pretend the circles are here. I just don't want them in the way right now, okay, because I want you to see what's happening. If this is the point r theta, that means that this is theta up from the polar axis, right? This is also a reference angle, isn't it? Well, if this is pi, and I go that same amount, I go in this direction, I go in the clockwise direction, that's the negative direction, then here would be the angle of pi minus theta. That's why they're saying pi minus theta. Got it? So if you replace theta with pi minus theta, and you get an equivalent equation, then the graph is symmetrical, WRT with respect to theta equals pi over 2. So in other words, if this is your r comma theta, then over here is your symmetrical point r comma theta minus, or pardon me, pi minus theta. Cool? And again, the circles are in there. I just didn't want them to like muck up the drawing. I needed you to kind of see just the drawing. Okay? So, pi, or theta equals pi over 2, that's basically the y-axis, isn't it? Polar axis is basically the x-axis, isn't it? Well, we had one more symmetry. We had the pole symmetry, didn't we? So if we take a look, the pole is located right here, isn't it? Which is basically the origin, isn't it? So now we're talking origin symmetry. By the way, let me back up here. Again, this is your y, and you're basically replacing it with a negative y. Got it? So here, if you remember from when we did origin symmetry for our rectangular equations, we replaced both x and y with a negative x and a negative y. So here they're saying replace r with negative r, or theta with theta plus pi. And you're like, theta plus pi, what? So let's say right here is r comma theta. Are you with me? Origin symmetry, if I was talking rectangular, tells me it should be over here. So check this out, right? Again, this is pi units. Basically your reference angle, excuse me. This is theta amount. This is basically your reference angle. Over here is pi, isn't it? Well, if I take my reference angle and head down this direction, isn't this a positive direction because I'm going counterclockwise? I'm going with the labeling of your axes. That's how they're saying here is pi plus theta. If you make this replacement and you get an equivalent equation, then this is symmetrical with respect to the pole, r comma pi plus theta. Got it? This one is, whoops, sorry, I forgot to put my negative here. Good catch. Thank you for telling me. This one is rather obvious. on these last two, it's understanding why you're replacing theta with pi minus theta, because you needed about this pi over 2 equal theta line, which in our rectangular system is the y-axis. And here, to replace theta with pi plus theta, because I needed it to be symmetrical about the pole, which is the origin in rectangular system, right? So we have to go basically into third quadrant, so pi plus theta to get me into third quadrant to get about the pole, and pi minus theta to get me into second quadrant to get around the pi over 2 line. Good? Okay, so stay tuned. I've got some examples of us working with polar equations and needing to graph them, but they're not so easy to graph, or I should say they're not so easy to change into rectangular form, so these symmetries are actually going to help us do some graphing. So hang in there. I'll be right back.